We're going to start chapter 2 with talking about just systems of measurements and how we measure things in this class. From here on out, any quantitative measurement that you express, whether it's in the lab or anything that we're talking about in class, should have both a number and a unit. 75 kilograms, 180 seconds, 3 times 10 to the 8th meters per second, 1,610 meters. So make sure that you're getting into the habit of expressing your measurements with units when you're reporting answers to pretty much anything that we're doing. SI-based units, we're going to talk a little bit about the SI system later, but for right now we're going to talk about a base unit and how that differs from derived unit. A base unit is one of the fundamental units that is defined arbitrarily. Arbitrarily means it was picked by somebody, a group of scientists. It's not based on combinations of other units. And the ones that are the most important to us are length, mass, time, temperature, and substance amount. The meter, the kilogram, the seconds, the Kelvin, and the mole. Those 5 units are the ones that you should know in terms of SI-based units. Ampere and light intensity, that's more of a physics concept, and you'll be dealing with those should you take physics after this class. The SI system, the System International, or the International System, is an international decimal system of weights and measures derived from and extending the metric system of units. So it's not exactly the same as the metric system, but it's very similar. Why do we use the SI system? It's international. Scientists can communicate with each other much more easily. It's decimal. It's based on denominations of 10. So you don't have to remember that there's 4 cups in a quarts. You don't have to remember that there's 5,280 feet in a mile. It's very easy to remember denominations of units. Temperature is a measure of the average kinetic energy of particles that are in a system. Again, these are particle level diagrams. These little arrows are showing how fast these little atoms are moving around in a box. Low temperature, low speed of those particles. High temperature, higher average speed. Particles become overall faster at higher temperatures. 3 temperature scales, one of which is terrible and we're never going to use, the Fahrenheit scale. Fahrenheit scale was developed by Lord Fahrenheit, and this is just a story. I don't know if it's actually true or not, but when he was calibrating his scale, he set 100 degrees to be the body temperature of a normal human. Well, he had a fever at that time, and that's why a normal body temperature is about 98.6, because he kind of screwed up that calibration of the measurement. I think it's just a good story, but it really just shows you how arbitrary the Fahrenheit scale is. A degree Fahrenheit is actually very tiny. A degree Celsius and a Kelvin are actually larger than a degree Fahrenheit. The most important thing about Celsius and Kelvin is they're both the same length. 100 degrees Celsius is the same temperature change as 100 Kelvins. Celsius was implemented because 0 degrees Celsius was when water freezes. 100 degrees was set as the boiling point of water, and it worked pretty well until we come down to this range. It can express negative quantities. When we get to topics later in the year, it doesn't make sense to express temperature as a negative scale because particles can either be moving or not moving. You can't have particles moving backwards in time. That doesn't really make sense. So therefore, it makes more sense to use an entirely positive temperature scale. So the Kelvin scale is absolute, which means at 0 Kelvin, everything stops moving. Beyond that, everything's a positive value. It can't go into the negative range. Furthermore, there's an easy conversion to go back and forth between Celsius and Kelvin. Take your Celsius temperature, add 273, bam, it's in Kelvin. So a Kelvin temperature is usually a little bit higher. Why are Kelvins used instead of degrees Celsius? It's because it's a positive, absolute temperature scale. These SI prefixes that I have in this table, you don't have to memorize them right now, but you will have to have them memorized by your first test and for the rest of the year. You should understand which units are bigger, which units are smaller. How many of one larger unit make up a smaller unit? This table summarizes those equivalencies, and these are the only prefixes that we're going to hold you accountable for this year. But really, you should just have a better sense of scale. So instead of doing some practice problems with converting units, we're going to start here with just some measurements. So I want you to take a minute, look at these three measurements and order them based on what you know about centimeters and meters and millimeters. Okay, well, there are 1,000 millimeters in a meter, and 900 millimeters is not quite a meter, so that would actually be the least. 200 centimeters. There's 100 centimeters in a meter, so therefore that's 2 meters, so that would actually be the largest measurement, and 1 meter would be in the middle. Sense of scale, being able to interpret these units and being able to really understand how big or small they are is going to be important for this class.